I'll hand it over to you two.
Yes, thank you. Yes, as you can see, we want to talk about how you can enhance an existing knowledge graph with keywords using large language models. I'm Valentin. I have previously worked at EQT Motherbrain as a machine learning engineer, and like Lele, I also left by now. On my part, I joined a young startup where we are building a music valuation engine in order to help rights holders to sell their music rights to music fans. But yes, I'm very happy to be back here to present this work that we did. And do you want to present yourself, Hans?
Yeah, so I'm Hans, and I'm at the Nobel Prize Outreach. We are the outreach arm of the Nobel Foundation. We work with websites, social media, and conferences around the world.
Thank you. And a lot of you might be curious, actually, how it came that Motherbrain collaborated with Nobel Prize Outreach. And to elaborate, it is because EQT is a partner organization of Nobel Prize Outreach. I believe together with some other companies like ABB and Scania. And yeah, I think Hans has met Alexandra Lutz, I believe, at one of the Nobel Prize events, who was our head of Motherbrain. And they realized that both of them are working on knowledge graphs and that they might want to collaborate on that. So that's how this came to happen. And you already know how Motherbrain works with knowledge graphs. Do you maybe want to elaborate, Hans, on how Nobel Prize Outreach works with knowledge graphs?
Yes, we have awarded the Nobel Prize to more than 1,000 laureates now. So yeah, now we're talking about graphs that is not millions, but a few thousands of nodes. But still, it's complex enough for us that we want to see how the laureates are connected to each other. What do they share? What kind of properties do they share with each other? How can we group them? How can we find relationships between them? And especially for a visitor at our museums or websites, how can you explore the universe of the Nobel laureates and navigate yourself among them? So we started to look into knowledge graphs 1.5 years ago and found that we had very little data, especially regarding the work fields of the Nobel laureates. And that was the start of this project.
Thank you. And this is why I also created this short overview. It's lagging a little bit again. About what the similarities we had in this research project. Because as you already see, we also build knowledge graphs at EQT about the companies and the sectors they are in and the geographies they operate in. And while all of this is very valuable, we often realize that this is not enough to make the predictions that we want to make, because we only constructed that with data that we could buy from different data vendors. But what would be even better if we would have information about what kind of products these companies sell, what services they offer, what business models they have. And this is why we would like to extract keywords that describe these aspects as well, that we then can add to this knowledge graph. And then the same in your case is that you already had a knowledge graph of the prizes and the laureates and also the universities they attended, for instance, which already was very informative, but it is even more insightful if you have information about what fields did they have impact in and what were their research interests in order to connect these laureates in a meaningful way. And this is why we realized that we have a common research question, which is how we can enrich an existing knowledge graph with novel and relevant keywords that meaningfully connect these entities that are in the knowledge graph. And this is how we came up with this method. And beforehand, actually, we experimented with a couple of other methods that were more like the standard that one would apply using topic modeling and clustering, and also using specific models that were designed only for extracting keywords. And that worked quite well and gave good insights, but of course we wanted to experiment with the most novel technology out there, for which we used then, of course, large language models. And to show how this went, we started with Wikidata, with a knowledge graph that we could extract from Wikidata. Then we used OpenAI large language models to extract keywords from additional data that we had available. And we realized that these keywords, they were of great quality, but they were often describing the same word in different ways. And this is why we realized we want to identify these different words that describe the same concept, those synonyms. We want to identify them and merge them in a common keyword. And once we did that, we added those to the existing knowledge graph and passed that on to Nobel Prize Outreach for quality review, which is what Hans will elaborate more on in a bit. Let's get started with Wikidata. And Wikidata is great for any one of you who wants to work with knowledge graphs and with data that is publicly available. I can very much recommend having a look at Wikidata. Actually, I saw Sukaina here earlier, who is a representative of Wikidata, I believe, but I think she might have left already, unfortunately. Wikidata is amazing because in our case, it contained a lot of information already about the Nobel Prizes and the laureates and the universities where we're affiliated with, where we have been working, and also the other awards that we have won, which is a very great starting point. And they even contained already fields of work in this Wikidata knowledge graph. However, we realized they were not always complete. For some more famous laureates, there were a lot of them, but for some, there were almost none fields of work. So that was not very helpful for us. And at the same time, those fields of work are also very generic and not specific enough. So we can see here that there is something like mathematics or formal science, which describes a lot of the laureates and isn't too specific to find smaller clusters. So this is why we came up with a very simple method, which was first only like literally prompting the language model, where we had some very valuable input from Hans, which were like the biographies and Nobel lectures, also press releases and ceremony speeches. And we could also get some Wikipedia articles of the laureates, of course. And then we simply provided these texts to the language model and prompted it to extract relevant keywords. We did have to be very specific there. First, we learned that, for example, a lot of laureates liked to do mountaineering in their free time, but this was not really what we were interested in. So we had to be, of course, very specific in defining what kind of keywords we want. And one idea actually that worked really well is that we requested a large language model to stick to terms that are present in these 7 scientific and political taxonomies that are listed here. And the relevant or the interesting part here is that we didn't actually need to provide the full taxonomy, but only the names of the taxonomies, because the language model actually knew, the language model already knew from pre-training more or less the terms present in these taxonomies. And then we used that to extract the keywords. And we plotted a histogram of these keywords, where you can see here on the y-axis the number of keywords, and on the x-axis you can see how many laureates these keywords are connected to. And I think what is most notable in this graph is that you can see this very high bar to the left of the graph, where we have about 3,000 keywords which are only connected to one laureate. But if we think about the goal that we had was to connect laureates in this knowledge graph in a meaningful way. But if a keyword is only connected to one single laureate, that is, of course, doesn't create any additional connection that is valuable to us. So what we realized is that we want to have, in this distribution, we want to have less of this high bar to the left and more higher bars in the right tail of this distribution. So this is why we went on with a method that we coined pairwise, standing for pairwise synonym embeddings, which was Lela's idea, the previous speaker. And it went in the following way, that we first, for each extracted keyword, we would use other2 to generate embeddings, which resulted in about 5,000 keyword embeddings. And then we would, for each keyword pair, we would calculate, using these extracted embeddings, the cosine similarity between both keywords, which then resulted in about 25 million similarity scores. And can I get an impression of the audience? How many of you are familiar with calculating cosine similarities between language embeddings? That's a very good amount. That's great. That's much more than I hoped for. In that case, I will not go more into detail here, but I think it's a very fundamental concept to understand for any one of you who is interested in working more with language models and especially with RAG systems, for example, because that is more or less the foundation what RAG models are based on. But so basically what we did next is that we ranked the keyword pairs by recursion similarity, which means that the most similar keywords were on top and the least similar keywords were on bottom. And this resulted in like the small screenshot that you can see to the right, where we see that it worked very well. For example, we had X-ray technology written once with a hyphen and without a hyphen as the most similar keyword pair, because it's literally exactly the same. And then if we looked further down on the list at a threshold of about 0.7, we saw that the terms are not exactly the same, but still very similar in their meaning. So this is why we set a threshold there and considered all keyword pairs above this threshold as synonym candidates. And it's important to notice that we wouldn't have needed to consider to take this threshold. We could have also just processed all 25 million keyword pairs in the next step, but we still did so simply because we wanted to reduce the amount of computation that we would have to do later on. So we would have only to process a small fraction of this 25 million keyword pairs. Exactly. So then, using that, we went on to the next step. And this was very simple, very simply prompted the language model to merge those both keyword input keywords into one merged keyword. And of course, it was still important to consider that even though we set this threshold, not all keyword pairs above this threshold were automatically synonyms. For example, it's always a matter of discussion, right? What is a synonym and what is not. But in this case, for example, click chemistry and bioorthogonal chemistry is something that we would not want to consider to be similar enough. So we did not only ask the large language model to merge the keywords into one, but also to say that if it doesn't agree that these terms are synonyms, then it should just return NA, and then we would not merge them. Yeah, and one interesting aspect actually that we could do if we would want to continue this process, that the new keyword, one option would be to pass it to ADA2 again to calculate a new embedding, and then use that in the next iteration of this. But another idea that we had actually is that in order to save some processing again, to save some energy consumption as well, we could simply take the average between the two input keyword embeddings and use that as embedding for the newly generated keyword. Yeah, and then this is what we did. And this again is the first distribution that I already showed before. And after one iteration, we can see that this distribution changed quite a bit, where it went the bar to the left went quite down, and to the right we have quite more elements now. And then, of course, we thought there are not only two ways of how you can write X-ray technology. You can also write X-rays. You can also write Röntgen rays or something like that. So this is why we realized if we just repeat this process one more time, we get even more synonyms merged and have even higher quality keywords. So that's what we did. And then we ended up here. And you can see that we have now much more keywords in this range that is interesting to us, between like 2 and 20 laureates that we are connected to. Yes, and then the last step was simply passing that on to add it to the existing knowledge graph, and then passing it on to Nobel Prize Outreach for the quality review, which was maybe even the most difficult part of this process.
So what was the outcome of this? Well, this is a small example of the keywords that we got from one of the laureates, a randomly selected laureate, Ada Jonat. And as a background in biology and structure biology, I can say that these keywords are really, really good. They are amazingly good. Question is, how good are they, and will the prize awarding institutions accept them? So in order to test that, I did a blind test. So I mixed some keywords that were created by experts, by the prize awarding institutions themselves. and these kind of keywords, and I submitted it as a blind study. And yes, there were actually some differences between the population that was curated by the experts and what we got from AI. And then it got really interesting. What are these differences? So one of the differences is that the prize awarding institutions are very specific in the wordings when they award the Nobel Prizes. They want to be very narrow in the way that they express the motivation of why they have awarded the Nobel Prize to a specific laureate. First, to make it specific in order to motivate it, but also not to exclude future Nobel Prizes. So they are extremely specific. That means they have that in mind when they look at the keywords. And if you then ask them to evaluate their own keywords with the AI-generated keywords, they will, of course, find a difference between them. So the learnings that we can make by this is that, okay, if we're going to expose these kind of keywords to a public in an exhibition at the museum or on a website and have it as text, then we should probably use some expert curated keywords or to check the AI-generated keywords. But on the other hand, the whole idea of keeping it so narrow as they want to do will sort of inhibit the making of a graph. So that is also why the strategy of using the AI-generated keywords are so important for us. The other difference that we found, and then looking at keywords that got a rather low rating by them, we found out that, okay, this is not associated directly to the reason why they were awarded the Nobel Prize. It could be work done before they were awarded the Nobel Prize. It could be that they improved the field, or that their research led to a new field, or actually that they opposed another field. So for them, that was not the proper description of the prize, but for us generating a graph, these are gold. This is exactly the kind of connections that we want to create between the laureates and the Nobel Prizes. So again, the learnings was that this AI system is really optimized for creating the relations that we want to have. But there is a drawback of it. In the AI-generated keywords, we don't know the nature of the connection. So we don't have the property of the connection. We don't know if they are opposing the field or working in the field. We don't know if it was a previous field or a current field and things like that. So that is something that we have to take into account when we use them. But that said, we got a very nice approval by the prize awarding institutions to use this strategy to generate keywords. They really, really liked the outcome of the keywords and the quality of it. The good thing is that it scales much more for us. We can generate more keywords. We can analyze much more texts compared to doing it manually. And it will really enhance our knowledge graph of the laureates. And as I said, they are also really optimized for finding relations and not a narrow scope of connection. Yes. So just to give you a few examples, this is a graph that is drawn from a manually curated keyword schema. And that is exactly what you described here in the beginning, Valentin, that you have sort of these very major fields and a few fields, a few keywords that you dedicate to the different laureates. So you have very few nodes, and you have a lot of laureates connected to these few nodes. So they are excellent in some use cases, but they are not so inspiring in exploration between the laureates. So this is the corresponding graph. Oh yeah, I should say that, oh, maybe I shouldn't go back. But in the center there was again Ada Jonat, the same laureate as you saw before. And this is the same laureate, Ada Jonat, but now it's a graph using the AI-generated keywords. And you see there are much more keywords. There are something like 10-fold more keywords that we get from the AI compared to what we had manually curated before. And we have a lot of connections between the laureates. So now we're really building a network that you can explore between the laureates and the Nobel Prizes. Should we see?
Yeah, we should be able to click on it. And not sure if it will show up on the screen share. No, I think it's loading.
Okay.
Maybe you speed up the internet.
Yeah. Well, that's promising.
Here we have it.
Yeah. Because it is a little bit easier to see when it's actually moving. So here I have Ada Jonat in the center of it. And you can see that there are actually quite a lot of connections between the laureates and different keywords here. So you can start to explore how they are connected to each other and how many laureates that share the different connections between the same. So this is a graph that invites you to much more explorations compared to the manual one. Okay.
Yeah, thank you very much. And yeah, I think the translation from screen to screen was lagging a bit. So I guess we can't make use of the full interactivity here today. But I think the concept came across. Yeah, thank you very much for paying attention.
Thank you. Thank you both. Any questions? Yeah?
So, to the best of your knowledge, does this generalize this deduplication? Are there libraries that do this? Because this is something, I mean, it comes up again and again. I've done this 2 times already in different projects. It seems like we should be able to develop something that we can sort of plug and play.
That's true, definitely. I'm not aware of any library, indeed. Indeed, of course, indeed, it's a very straightforward and even obvious idea to do exactly that. And it's definitely that we were not the first ones who had that problem as well, right? So I think we should do that, yeah.
Let's do it.
Yeah, let's do it.
Yeah.
Yep. Sakina?
Yeah, and here is our Wikidata representative, by the way.
Exactly. So
Excuse me for not running you ahead.
I had an urgent call, that's why I didn't show up when my name was mentioned. But I have actually, first of all, that's an amazing presentation, great work. I have actually 2 main questions related to Wikidata, of course. The first one is, what kind of blocking point did you face when dealing with this database? And the second point is, did you rely on the data that was already there, or have you uploaded your own by being, you know, an active user on Wikidata? So these are like my 2 main questions.
The second one, no, we have relied on the data that was already in Wikidata. What was the first question? Do you mean if you had any process in processing the amount of data?
No, like dealing with Wikidata itself. Was it like, did you face any challenges or like blocking point? How was your experience with Wikidata? Yeah.
I see. Thank you for that question. Honestly, I was very positively surprised. Not sure if I can still share my screen, but there is like this Wikidata query service, which I think now it almost feels like an advertisement session, but I think it's at query.wikidata.com or something. Yeah. And it's amazing. It's like you write a small SparkQL query and you directly get this like this like graph that you want to extract. And I think to be fair, also like co-piloting this with like ChatGPT made it much easier, right? I think given that I didn't have experience with SparkQL before, I would have been very difficult for me to figure out how to write these queries myself, and especially also even how to figure out the right Wikidata entity. That would not have been that easy. And also the Wikidata relations, but actually like, yeah, co-piloting that with ChatGPT helped a lot. So I think, yeah, I can just show it. I can't write a SparkQL query on spot now,
And while you do that,
It
I
should
can
be,
say that at Nobel, we are trying to collaborate quite a lot with Wikidata and Wikipedia. So we share unique identifiers between us for Nobel laureates. And when we announce the new Nobel laureates, as we did last week, we have it in our data set the same second as we release the press releases on the web. So yeah, we have a connection between our databases.
That's nice to hear. Just something maybe to share from my side is that usually Wikidata, like we have a very nice querying system that makes it easy, but not all the data is well structured. I think the noble personalities or like winners are like well structured because this topic itself has a lot of people on Wikidata working on it. So there's already like a model set in place and everyone respects that when they want to add a new entity to that database, which is, I think, a very positive point that facilitate the work on this project. But different topics or like different data items, it usually turns out to be very difficult because the structure is not there. And then we introduce to these kind of projects to kind of set up a structure and force it as admins so that no one can just go and add, entities as they want. But yeah, I think for Nobel Prize and these kind of linked items, they are like well structured. So good that was a point for this project.
Yeah,
cool.
And we at Nobel do not edit the data ourselves in Wikidata, Wikipedia, but we use it and we refer to it, and it's also included in our knowledge graph.
Cool, good to know.
Yeah, actually, I realized it's wikidata.org, importantly. But now I think the connection is too slow and yeah. But you can try it at home. And I think to answer actually the question, the most difficult part was to figure out how to find all of that, right? That's always when you start working with a new tool, right? Where actually can you find all of those things? And also actually the connection with Nobel Prize. I think there's also a site where you can see all the documentation regarding the Nobel Prize server and Wikidata connections. Once you find it, it's really easy.
Popped up now, but
amazing. This is it.
we have Drew again.
Yeah, I was just wondering why you stopped at 2 iterations for this, the merging. Was there some heuristic you used, or you just looked good enough and you were happy with it?
Exactly, the second one. It was, we realized the first iteration was already quite good, but there were some cases where we thought, oh, that could still be improved. So we went on to the second iteration. And then we already saw also, we already created a lot of keywords like that. On the plot, on the chart that I showed, it actually didn't look like a lot because just the scale was off because I wanted to show the difference to the 3000 at the beginning. But actually there were a lot of, there were like already some, I think, at least 1,000 keywords that were connected to 2 to 20 laureates, and that already created a lot of connectivity, as you could see also on that graph. That were already a lot of keywords. We could have done even more iteration and we would have gotten even more keywords, but we were happy with the quality and also with the quantity of keywords that we extracted so far. But of course, if, for example, NPO would have come with the feedback that we wanted more keywords, we could do another iteration.
Thank you.
We have one more question here.
So I remember the charts with the keyword occurrences was one outlier to the right, the 40 occurrences. What was that? Was it Nobel Prize or?
I forgot what it was by now. I haven't looked at that again. It was a very obvious term, definitely.
Scientist.
Something like metaphysics.
Oh, okay.
Something like that. Yeah.
Thank you for the presentation. What have you been able to use this knowledge graph for, like in practical terms? Like what kind of like features or how have users benefited from this?
That remains to be seen. It's quite new. So what I'm doing right now is that I'm creating proof of concept visualizations like the ones you saw here. I'm going to include a lot of things from our graph to combine the different graphs together, allow you to query the graph, things like that. I'm also going to build a timeline based on it, because we have time information when the prize was awarded, the year of the discovery, things like that. So you could actually build a timeline on when the different keywords appeared and disappeared, like a field building up and going down, and also how specific keywords has occurred at different prices in time. So that's my next steps, and that will be sort of an exploratory tool within the Nobel for creating stories. We're trying to create a lot of stories for our social media and for our web, for the exhibitions in the museums, things like that. So it will at first be an internal tool there. We're also collaborating with the Visualization Center in Norrköping that creates publicly visualizations like the Doma Tekniska Museum. And they are going to build a graph explorer for the public. And we hope to have that in a museum and maybe also on websites.
Very cool.
All right, I think we stop here and have another 15-minute break. So maybe another round of applause for Hans and Valentin.